Welcome to the port of Rotterdam, the biggest port of Europe where the river flows into the Atlantic Sea. This is a delta, which is one of the most important wetlands for climate change mitigation. First things first, let's start with a dive into what a delta is. Deltas are an important type of wetland. Deltas are the boundary between water and land, where rivers dump their water and sediments into lakes, rivers and oceans, and sometimes even onto land. Sediment has to be deposited for a delta, so a slow current and waves and tides that do not sweep away everything immediately are crucial. There are roughly three types of deltas: river, tidal and wave-dominated deltas. Firstly, the river-dominated delta. They have more silt build-up than is being washed away by the waves and the tides. The river transports a lot of sediments that is deposited, resulting in very fertile land. Secondly, the tidal dominant deltas. Naturally, these are the most prominent when there's a large difference between low and high tide. The tides redistribute the sediments, making ridges or islands in the water. These are also important for ecosystems such as mangroves and salt marshes. Lastly, we have wave-dominated deltas, where the waves shape the delta. They typically have a smooth coast with dunes, as the waves deposit and take away the sand along the coast. Deltas are unique biotopes, with a lot of nutrients and sediments due to erosion along the coast, which is picked up by the rivers. It's a place where salt and fresh water meet, attracting all sorts of wildlife. The wildlife depend on the type of delta, the climate, but also on human influences. Speaking of humans, about 4.5% of humans live in the delta region, and even more are dependent on resources gathered from and around deltas. Deltas are also important climate change mitigators. They store enormous amounts of carbon. They even store carbon in the longer cycle, which can take millions of years to become CO2 again. But how does carbon get stored in the longer carbon cycles in deltas? Let's take a look. We began our journey at the start of the Rhine and the Meuse River. That is also the starting point of where a lot of nutrients and organic carbon come from, which are transported by rivers and end up in the delta. Organic carbon is any molecule with carbon in it that is produced by autotrophs, like glucose. This organic carbon can sink and get buried by sediments, resulting in carbon preservation. This burial process is not exclusive to deltas. It happens in all the oceans and all the rivers. Nevertheless, deltas bury more carbon because the rivers take a lot of terrestrial carbon and sediments with them. They usually are more shallow, so they have less space and time to degrade organic carbon, and have more sediment that can bury the organic carbon. About 80% of all organic carbon preservation in marine sediments happen in and around deltas. Let's zoom in this burial process. Imagine an organic carbon particle flowing in the sea. In order to bury it, the particle has to reach the seafloor, which is more difficult than you would expect. A lot of tiny organisms and microbes live in the oceans that will try to eat the organic carbon. If they do so, they produce inorganic carbon that will go into the short carbon cycle. Bigger organic particles will sink faster and have a higher chance of reaching the seafloor. For an even higher chance of reaching the sea bottom, the organic particle can hold on to sediment particles. The better the organic particles and sediments hold on to each other, the better sediments protect the organic carbon from microbes and degradation. Smaller sediment particles like clays and silts have a better hold on because they have a bigger surface area in relation to their size. Surprisingly, the organic carbon particle reaches the bottom of the sea unhurt, but it's not buried yet. At the seafloor, it can still be blown away by a water current or eaten by microbes and microorganisms. Even if sediment layers bury the particle, it is not yet preserved. For that to happen, the particle must make its way through microbes that live in the soil, to end up so deep that it's too hot for living organisms to survive. Only a fraction of a percent of all organic matter in the world get past all these obstacles and get preserved. However, the exact number that is preserved depends on a lot of local conditions. What local environment can change the organic carbon rate? Oxygen levels of the water are thought to have a big influence on the organic carbon burial rate, because oxygen levels influence the microbes that live there and their metabolic pathways. A common perception is that microbes that respire using oxygen are better at degrading organic carbon than microbes that live in anoxic conditions. Thus, that anoxic conditions would lead to more preservation. However, it has been shown that anaerobic microbes are just as efficient as the aerobic ones. A reason why more carbon burial is found under anoxic conditions may be because there is more macrofauna present in oxic zones, which disturb the sediment, releasing the organic carbon particles. Moreover, anoxic environments can be caused by algal blooms. These algae and plankton produce enormous amount of organic matter. So, there is more than can be broken down. All of the oxygen is used by the organisms to break down the organic carbon. So these organisms will die because they have no oxygen left. But there is still a lot of organic carbon which cannot be broken down because the organisms that's supposed to break down the carbon are dead. This remaining organic carbon can be buried and preserved without obstacles. But how do algal bloom happen? Algal blooms can happen due to the excess amount of fertilizers and nutrients and results in deaths of all living organisms in that area. They become more common as people use fertilizers, dump nutrient-rich wastewater in rivers, and cut down forests along rivers. Another local environmental condition is the presence of plants in the river delta. Plants also sequester carbon, but by growing in the water it's easier for them to get buried, burying the organic carbon with them. Plants take in inorganic carbon to produce oxygen, thereby making anoxic conditions less likely. There are also risks. Too many plants will have the same effects as algal blooms and can restrict recreation. Throughout this video we have painted inorganic carbon as the bad guys, which is not the complete truth. Inorganic carbon can go back to the atmosphere, but can also become carbonate, which is a mineral. This mineralization is also a form of long-term storage of carbon. In the end, the most important factor in carbon burial and preservation is the amount of sedimentation. The more sedimentation, the more burial. At the moment, deltas all over the world are sinking. Less sediment is reaching the deltas due to dams and more nutrients are piling up in the sea via sluices. That's not all. A lot of bottom trawlers are used to fish. These trawlers destroy the seafloor, disrupting the carbon barrier process and killing marine life. There's also some hope for news though. There are experiments being done to see whether we can enhance carbon sequestration by putting sediments, rocks and minerals in the ocean. An example of a mineral is olivine, which takes up CO2, makes the oceans less acidic and helps with inorganic and organic carbon burial. There's also environmental risks, such as the release of heavy metals, and it's crazy expensive. All in all, there are many intertwined processes with the deltas, making it impossible to go over everything. We mainly want to convey how complex these marine ecosystems are, and that enhancing carbon sequestration in deltas is challenging and is not the solution to climate change. There should be action taken to protect these deltas, for the life that these rare biotopes support, and for the preservation of carbon. Thank you for watching, and if you got curious and want to know more, we put other YouTube videos, research papers and websites in the description. Thank you.